All right, folks, these are the solutions to equilibrium. Problem set 2, objects hanging from ropes. More practice. These are classic problems. Um, okay, so you're given the mass is 2 kilograms. What is the tension in string 1? So I'm going to draw the force diagram over here. In your miscellaneous column, you might want to calculate the weight of the block. So 2 kilograms times 9.8 is 19.6 newtons. It's a little confusing because that is the weight, which is, we know, being balanced by the tension. But if you were drawing the force diagram, so the tension equals, so kind of transitive property, the weight is 19.6. This weight isn't moving, so the tension is 19.6 newtons. So drawing all the forces at the knot, the tension is up on the block but down on the knot. So we know this rope is stressed by 19.6 newtons. And then we have sorry, this right in the way of my color picking. All right. And then this rope is pulling this way and this way. We don't care about the stress on the wall. We just want this one. That's T1. We don't know what it is. And then this rope is pulling crooked and crooked. They give you that angle up there, which is the same as this angle down here. So this is T2, 30 degrees. Okay, so what we've done so far is miscellaneous column, get that weight so it's not mucking up. You got enough going on over here. Draw all the forces. Technically, this is tension. I would really like you to label that tension. That knot just knows there's 3 different ropes pulling. Okay, so we have 3 different ropes, so we have 3 different tensions. Then break down T2. The magnitude is always the actual stress. This angle 30 degrees is making contact with this leg. So this is T2 cos 30 and T2 sine of 30. And then let's color code all the up and down forces in green. So we have 1, 2 up and down forces. That's not too bad. And then all of the left and right forces in pink. We have 1, or purple, 2, not too bad either. Okay, so we know more about the vertical, right? Because we know this 19.6. So let's do the vertical column first. The forces are balanced, and I have 2 green vectors. So I have T2 sine of 30, which is pointing up. So that's positive. Minus the 19.6, which is really a tension, not the weight. It happens to equal the weight, but it's really a tension. All the knot knows is that the rope molecules are pulling down. So that tells you T2 is 19.6 over sine of 30, which is 39.2. So now we know the magnitude of this is 39.2, which will let us find the horizontal part, this purple thing right here. So horizontally, the sum of the forces is 0. So I have T2 cos 30 pulling to the right, so that's positive, minus T1 that I don't have to break down because it's completely flat. It is horizontal, and those are balanced. So plug in now 39.2 cos 30, bring that over to the other side, equals T1. So T1 equals 30, pretty much 34 newtons. Okay, I'm going to quickly, and then you can chapter to the next question. Sometimes, even though this makes it easier that we don't have to break it down, sometimes people find that confusing. So you could say left and right is T1 cosine of 0 degrees, which is just T1. And then up and down is T1 sine of 0 degrees, which is 0. Okay, so if you're someone who likes, order, repetition, and you want to do the same thing every time, technically we are doing cosine and sine, but cosine of 0 is 1 and sine of 0 is 0. Okay, so that was, oh, sorry, what's the answer? The answer is C34. Okay, look at this hint. Note, this is a tedious two equation, two unknowns problem. I got these problems from the textbook for college professors who want to give multiple choice because they've got 120 people in the class and they got to do multiple choice. So what do we know? The mass is 60 kilograms. So let's go to our miscellaneous column and say force of the weight equals mg equals 6 times 9.8 or 58.8 newtons. And we want the tension in string 1, but we're going to get two equations, two unknowns. Let's see, let's draw the force diagram here. So the tension T3 is balancing the weight. So again, please label it tension. But just like the scales can be tricked to measure the weight, even though they're recording the pressure, this is really tension. It is pulling down on the knot and up on the block. And it's pulling up on the block equal to its weight, so therefore it's pulling down on the knot with the same amount. Okay, so that's your T3. T1, this angle, which is 30 degrees. So you have two options. This angle is making contact with this leg, so the vertical for this is actually T1 cos 30 because the angle indicator is making contact with this leg. So that's your cosine leg, and this is T1 sine of 30. Okay, so the mnemonic that's always going to work is the angle is making contact with this leg, so that's your cosine. If you don't like that, which is completely fine, you can say 30 is just the quote wrong angle. So you can say, I like the cosine stop sign mnemonic, but it only works if I know the angle relative to the x-axis. So if that's 30, and I hate that these add to 90, this is 60 just because that has to be a right angle. So if that's 30, that's 60, not because that one's 60. Okay, so this is T1 cosine 60 because now this 60 degrees is making contact with this leg. So this is T1 cos 60. And all right, so it's pulling to the left with T1 cos 60 and it's pulling up with T1 sine 60. Okay. And then T2 is shallow, and that is 60, which is the quote wrong angle because it's relative to the vertical. So again, I hate that these two add to 90 coincidentally. But I want that angle, so 30 degrees is now making contact with this leg of the triangle. So that's T2 cos 30 and T2 sine 30. All right, now, how many left and right forces do we have? 1, 2. How many up and down forces do we have? 1, 2, 3. So do we know, again, we don't actually have more information in either the horizontal and vertical. So let's see, I'm just going to match my key, which I'm following along with. Okay, so horizontally, the forces are balanced. I like doing the plus minus, so then you can see this vector's pointing to the positive, so that's positive. So we have T2 cos 30 minus T1 cos 60 equals 0 because those two forces are equal, those components. So T2 cos 30 equals T1 cos 60. So I guess because we tend to solve things here, like you could divide, but you could solve for T1. So, oops. So T2 equals T1 cos 60 over cos 30, right? Haven't solved the problem yet, but that's okay. We have another column to do. So that's just the information in the horizontal column. And then in the vertical column, forces are also balanced. But I have 3 forces. T2 sine 30 pointing up, so that's positive. T1 sine 60 pointing up, so that's positive. T3 pointing 100% straight down, so that's negative. So we have T2 sine 30 plus T1 sine of 60 minus 58.8 equals 0. Then we have already solved for T2, so plug that in. Be careful, don't drop the sine of 30. And then that gives us, I guess we'll keep it in green. That gives you T1 cos 60 over cos 30 times sine 30. All of that. Because that just went in for T2. And then we have plus T1 sine of 60. I'm going to bring this over to the other side, equals 58.8. Okay, we're in the home stretch. We only have a single variable left here. So I did multiply this out. This turns into 0.866 T1. This turns into, I'm going to check that. All right. I thought that didn't seem right. So this turns into 0.289 T1. This turns into 0.866 T1 equals 58.8. Combine those two terms, divide by that total. So T1 is 50.93 newtons. And then super plug and chug. Take that, plug it in here. So T2 equals 50.93 times the cosine of 60 divided by the cosine of 30, and you get, oh, I guess we didn't care. We just wanted T1. And so T1 was 51 newtons. Okay, a lot of algebra. Okay, I specifically assigned this one because this rope is in the 3rd quadrant, so you want to be careful with your plus and minus signs. So I'm not going to talk through as much of the math, some of the procedures, because I've already done that. So you can use your miscellaneous column to calculate the force of the weight, which is 10.78 newtons. Again, I'm kind of, I want to focus on the signs of things. So let's see, let's draw the force diagram here. So that's the weight. which means this tension in this vertical rope here needs to balance that. So T3 is 10.78 newtons. And this rope is pulling this way and this way. We don't care about the force on the wall, but I'm just going to make it really big so we can see the vector breakdown. That's T1, and this is 40 degrees. That is relative to the horizon, or that is making contact with, the angle definition is making contact with this leg. So that means the rope is pulling to the left with a force of T1 cos 40. And it is pulling down with a force of T1 sine of 40. Okay, and this other rope is stressed. So there's a T2 going up on the knot, crooked on the knot, and crooked on the ceiling. We don't care about the ceiling. So we've got T2, they gave you the wrong angle. That's relative to the vertical. The dashed lines are vertical, so that reference is relative to the vertical. We don't want that, or at least I think we don't want that. If that's 40 degrees, then this is 50. And now the angle is close, the angle definition 50 is closer to this side, so that is your cosine. And then, dang it, why do I do that? This whole vertical leg is the whole thing is T2 sine of 50. Okay, so a little bit tricky. Hopefully your drawing is better than mine. Again, we have 1, 2, 3 up and down forces and 1, 2 left and right forces. All right, so let's do our left and right forces because there are fewer of them. The forces are balanced. So we have T2 cos 50 pointing to the right minus T1 cos 40 going left. Nobody is winning. So T2 is going to be T1 cos 40 over cos 50. We've done that a million times, so hopefully that makes sense where that came from. That's my horizontal. We're stuck, so we're going to go to the vertical and say up and down forces also balanced. This is why I wanted to assign this problem. We have T2 sine 50. That's going up. It is pointing to the positive. We have the weight, or sorry, it's not weight. We have the tension 3 pulling down. And they told us, we calculated that. And then we have T1 sine 40 also going down. And nobody's winning, so they add to 0. So this was going down, whereas in the previous problems it was going up. Okay, all that means is you have a minus sign here. Okay, we're going to plug this in for T2. So I'm going to get we got a cos 40 over a cos 50 times a sine of 50 minus 10.78 minus T1 sine 40 equals 0. Okay. All right. So then we have all of this. Yeah, I'll calculate it. Sorry. Okay, all of this turns into 0.9129 minus the 10.78 minus, I dropped the T1, minus 0.643 times T1 equals 0. So now we want to take 0.9129 minus the 0.643. which turns into 0.270 T1. Bring that over to the other side, equals 10.78 newtons. Okay, so hopefully you see where all that stuff came from. Boom, boom. So T1 is 10.78 newtons over 0.270, which is 39.9 newtons, so almost 40 newtons. And so they're rounding to 2 sig figs. So that was T1. Luckily, it asked for T1, and that's what we solved for. All right, so lots of algebra. If your algebra is good, you know, decide how much time you want to spend on that. But again, the moral of the story for this one is don't be afraid for forces to be in the fourth quadrant. Okay, this one is tricky because of the symmetry. So I'm going to explain the force diagram that I have in the paper answers. And if that's all you need, then, you know, clearly you can pause the video. Okay, I have put problems like this on the test before because I think it's important to understand what's going on. But hopefully you've watched enough of these that you know that I'm going to call this T3 is pulling up on the weight with some value we don't know because that's what we're trying to find, up on the weight and down on the knot. And this rope 2 is pulling to the right on this side and to the left on this side. And T1 is pulling in the second quadrant and on the ceiling. And I'm running out of colors. T4 is pulling down on this knot and up on that weight. And T3 is pulling first quadrant and down on the ceiling. Okay, so I'm running out. I didn't draw the matching tensions for these guys because the block is too close. So it looks like there's way too much going on, but by symmetry, these two tensions are equal, and these two tensions are equal. Like, maybe I'm not being clear. Like, it doesn't matter which knot you look at. What do we care about? We want the mass. The masses are the same. T3 is equal to T1 in magnitude. Totally different directions, and T2 is equal to T2. So the reason we call it a free body diagram is you can isolate this knot. Oops, we don't even want the ceiling. You can isolate this knot and you really only have 3 forces that you care about. Or you can isolate this knot and you only have 3 forces that you care about. And since these are both the same M, it doesn't matter which one you look at, it's going to be the same. Okay, so in the paper answers, I looked at the left knot. You could look at the right knot, you should get the exact same thing. But that, to me, is the tricky part, is recognizing this looks way really super complicated. I only have to look at one of these 2 knots because everything else is a mirror image. And so therefore, if I know all of these forces, I know all of those forces. Okay, hopefully that makes sense. Okay, so I looked at this one, and there's a tension here that happens to equal the weight, just like the normal force happens to equal the weight, but it's not necessarily it isn't caused by it isn't the weight. You know that T2 is 30 newtons. That was given. And then we have a crooked vector T1, and alpha is 40 degrees. And so by alternate interior angles, that is 40. So that 40 degrees is making contact with this leg. So that's T1 cos 40. And And this vertical is T1 sine 40. All right, and then I've got two horizontal forces. You got to have at least two, right? You can't add to zero unless you've got one positive and one negative. And I have, here's a vertical, here's a vertical. So I have two verticals because this T2 is totally flat. Okay, so here you know more information horizontally, so let's do that column first. And that may be all we need to do, we'll see, plus or minus. Okay, so we're going to do horizontally. Sum of the forces add to zero because it is forces are balanced. Equilibrium. We have 30 newtons pushing to the right, so that's positive. We have only part of T1 pushing left. So T cos 40 equals 30. So T equals 30 over cos 40, which is 39.16 newtons. Is that all we care about? Nope. Oops, I dropped the which tension is this? This is T1. So we know this is 39.16 newtons. We want to know, I think I call this T3. We want to know T3. So let's go to the vertical column and say those forces add to zero. So I have T1 sine of 40. It's out of screen, out of view, but that's this. We have T1 sine 40 up. This was 100% vertical, so nothing from that orange vector, but the T3 is down. And those are balanced. I found out what T1 was, so we can plug that in. Equals T3, so T3 is 25.17 newtons. Not quite done. Thank you for your patience. If we look at the mass, if we focus on this instead of the knot, then we have the weight and we have T3. So it's pulling up on the weight and down on the knot. But it's the same magnitude because the rope molecules are stressed the same amount. These two are equal to each other because this is an equilibrium. So a positive 25.17 minus mg is balanced. So the mass is 25.17 over 9.8, which is 2.57 kilograms, which is answer C. Okay, so the trick on this one was that the system had symmetry. So you could use that and only focus on one of the two knots, but that was kind of tricky and one until you've seen it once. So that might happen more than once in this class where you're like, I never would have thought of doing that. But the first person who did this also wasn't, trying to fit in this problem solving in, half hour increments on top of all the other stuff you have to going on. So might have taken them a long time to figure it out. Once you see this trick, hopefully you'll remember it. And again, that's just don't compare yourself oh my God, Miss Groppy did this in 15 minutes. The first person who figured this out took them more than 15 minutes, if that makes sense. That has happened to me multiple times. You're like, oh, I never would have thought of this trick. Once you see it, you're like, okay, I can now recognize this trick, even though I didn't come up with it myself immediately.